Hello guys, what's up? How you all are doing? Welcome to Mathology Overflow, the second video. Let's get started. Let's look at the new variant of problems. The first one, we toss a coin 5 times. How many different sequences of heads and tails are possible? The sequence here means H, 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 or it could be H, T, T, H, T, or it could be T, 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 etc. Let's denote the head as H and the tail as T. So every coin toss has 2 outcomes. Either it will be a head or a tail, and there are 5 tosses. Also, please note that the outcome of toss 1 does not affect the outcome of toss 2. A head or tail in toss 1 does not affect, impact, or influence if there is going to be a head or a tail in toss 2. Hence, the choices for each coin toss are independent. So, if we denote the coin toss is 1, 2, 3, 4, 5, there are 2 choices, head or tail, for coin toss 1. There are 2 choices for coin toss 2, 2 for coin toss 3, 2 for coin toss 4, and 2 for coin toss 5, right? Let's try to visualize the sequences by drawing the tree. Toss 1, toss 2, toss 3, toss 4, toss 5. Let's start drawing the tree, assuming the choice for the coin toss 1 was a head. So this will have 2 outcomes for coin toss 2, a head and a tail. This, on the other hand, will have a head and a tail. This will have a head and a tail. This will have a head and a tail. Similarly for these 2 as well. And these one will have head and tails as choices for coin toss 5. If you see closely, if we fix the choice of toss 1 as head, we will have 16 different outcomes over here. We can visualize the sequence as this one as one sequence, this one as another sequence. Similarly, H, H, T, H, H is another sequence. H, H, T, H, T is another sequence. If we move across from toss 1 to toss 5 via these links and we take the vertices or the nodes and then concatenate the letters H, 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 we will have our sequence. Similarly, we can have H, 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 T, H, and so on and so forth. So this, just for H as a choice for toss 1, we will have 16 possible sequences in total. Also, please keep in mind, along with the choice H for toss 1, we also have the choice T for toss 1. You can try it out yourself that T as a choice for toss 1 will also have 16 possible sequences. Well, exactly identical to this particular part for 16 possible sequences. So in total, you would have 16 plus 16, 32 sequences. Let's go back and try to complete it in another way. So you have 5 coin types. 1, 2, 3, 4, 5. And each of them has 2 choices. Coin toss 1 has 2 options. This one has 2 options. 3 has 2 options, 4 has 2 options, as well as 5 has 2 options. So in total, and since the choices are independent, you have 2 times 2 times 2 times 2 times 2, 2 to the power of 5, which is 32. Over to the next problem. So there's a 8x8 board and every cell can be colored either black or white. How many such colorings are possible? So there's a 8x8 board. So the total number of cells in the board are 64. Now every cell has two choices, either to be colored black or white. And the choices are independent for each and every cell. So it's pretty much similar. We did a very simpler variant in the previous problem where we tossed a coin 5 times and every time we had two choices. However, in this case, we can equivalently translate this problem as 64 coin tosses. Every time you would have two choices. So in this case as well, you would have two choices for every cell. So in total, you have 2 to the power 64 possible colorings. Jumping on to the next problem. We call a number even if all the digits are even but not 0. How many 6-digit even numbers are there? So all the digits are even. So let's first note down the even digits. It's 0, 2, 4, 6, 8. There are 5 even digits possible, but 0 is not allowed. So our allowed set of digits are 2, 4, 6 and 8, which is 4. Now we are being asked how many 6-digit even numbers are possible. So if these are my digits, 1, 2, 3, 4, 5, 6. Every digit has 4 choices. So digit 1 can have 2, 4, 6, 8. Similarly, digit 2 can have 2, 4, 6, 8 as the possible choices. For digit 3, digit 4, digit 5, digit 6 all have the same 4 possible choices. So, and the choices are independent. Having a 2, 4, 6, 8 in place of digit 1 doesn't impact or affect having a 2, 4, 6, 8 in digit place 2. So the total number of possibilities are 4 times 4 times 4 times 4 times 4 times 4, 4 to the power 6. Before moving on to the next problem, let's just quickly try out a variant of this problem. In this problem, we have mentioned that 0 is not allowed. What if 0 was allowed? So you have 6-digit even numbers. All the digits are even. So this is your all the possible choices. So you have 5 possible choices. And this is your 6-digit number. However, for the first place, can we have 5 choices? Can we have a 6-digit number starting with 0? No. We can only have 4 choices for the first place. 2, 4, 6, 8. But for all the other places, the possible number of choices are 0, 2, 4, 6, 8. So the first place have 4 choices. Place 2 has 5. Place 3 has 5. Place 4 has 5. Place 5 has 5. Place 6 has 5 choices. And the choices are independent. So we multiply all of the possible choices and we get 4 times 5 to the power 5 as our answer. So this was a slight variant of problem 0.16. Well, that was all about the previous problem. The next problem seems to talk about a language, Bengali, which has 50 letters. Trisha, being a 6-year-old, can write Bengali words with no more than 5 letters. How many such words can Trisha come up with? So before delving deep into the problem, we should first think about this particular phrase, no more. What does that actually mean? Let's take a look. This particular phrase, no more, means either that's the maximum or at most. We can say let x be some variable which can take, let's write this down. Let's take an example. X is a variable which can take no more than 5 values. So no more is something which means that's the maximum limit. Usually in mathematical problems, we tend to use the phrase at most a lot. Both of these 3 things nearly means the same. Now let's see how does this phrase changes the problem. So Trisha, being a 6-year-old, can write Bengali words with no more than 5 letters, which means Trisha, being a 6-year-old, can write Bengali words with at most 5 letters. Now the main question is how many such words Trisha can come up with. Alright, so let's break it down into few chunks. Trisha can write a word with 1 letter. Trisha can write a word with 2 letters. Trisha can write a word with 3 letters. Trisha can write a word with 4 letters. Trisha can write a word with 5 letters. Now, for each of the cases, you need to find out how many such words are possible. So let's try to figure out. So this is the number of letters and this is the number of possible ways, right? So for 1 letter, right, you have 50 possible choices. For 2 letters, both of the places have 50 possible choices. Keep in mind, the choice of a letter for the first place doesn't impact or affect the choice of the letter for the second place. Hence, that means both of the choices are independent. So there are 50 times 50, 50 square possible choices. Alright, time for the number of possible words with 3 letters. Well, the first place, 50 choices, the second one, 50 as well, and the third one, 50 as well. So this is 50 cubed. For the words with 4 letters, you have 50 to the power 4 number of ways with similar explanation. And for the words with 5 letters, you have 50 to the power 5. Now let's look at the question once again. How many words can Trisha come up with? She can come up with a word with 1 letter, or she can come up with a word of 2 letters, or she can come up with a word of 3 letters, or she can come up with a word of 4 letters, or she can come up with a word of 5 letters. We can write this as 1 letters, 2 letters, or 3 letters, or 4 letters, or 5 letters. Since it's an or over here, we need to sum this thing up. So the total number of ways or the total number of words that Trisha can come up with is 50 plus 50 square plus 50 cube plus 50 to the power 4 plus 50 to the power 5. This is the solution to this problem. What if we would have replaced this phrase no more than 5 letters with exact 5 letters? If we replace the last part, no more than 5 letters, with something like exactly 5 letters, how would the solution change? Keep in mind, here we are looking for exact 5 letters. So in that case, the solution would be just the possible number of ways to create a word with 5 letters. That's 50, 50 for the second one, 50 for the third one, 50 for the fourth one, and 50 choices for the 5th place. So in total, as the choices are independent, as we have seen previously, it's 50 to the power 5. So I guess you guys could understand the difference between the solution of this problem and if we replace the phrase no more than 5 letters with exactly 5 letters, how would the solution change? So this was an interesting problem. Let's move on to the next problem, a new variant of the same style of problems. 0.18 states that John wants to start an exclusive club where for every member there's a card which has 3 digits. He wants to compute the number of members of the club if the club... Alright, so every card has 3 digits, and for the first subpart of this problem, he just wants to compute the number of members of the club. So you have 3 places, and what are the possible choices for this particular place? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 possible choices for this place. Please note there is no constraints on how the 3-digit numbers should be for each of the members of the club. So that's why I am assuming it can start with 0. Obviously, the choice of the digit for the first place doesn't impact the choice of the digit for the second place. So the second place has the same number of choices, 10. The third place also has the same number of choices, 10. So since the choices are independent, so the total number of members of this club is 10 times 10 times 10, which is 10 cubed. Let's see the second subpart. The club doesn't have the capacity of having so many members, so he self-imposed restriction that 0 and 7 are not allowed as digits. In this part, the number of digits will shrink down from 10 to 8 as 0 and 7 are not allowed. So the new set of digits that are allowed for all those 3 places of the member card is 1, 2, 3, 4, 5, 6, 8 and 9. The choices are independent, so the total number of members now would be 8 cubed. What if he doesn't allow 3 digits to be, what if he doesn't allow 3 digits in the member card? So the total number of digits that's possible is 10. He isn't allowing 3 of them. So there are 7 choices for every place of that 3-digit card. Every place can be filled up with 7 choices. And choices are independent, so it's 7 times 7 times 7, that's 7 cubed. Similarly, if it doesn't allow 4 digits, then you have 6 possible choices for each of those places, and total number of cards possible is 6 cubed. Similarly, if he doesn't allow 5 digits, then it's 5 cubed. It doesn't allow 6 digits. The number of cards shrink down to 4 cubed. So that was all about this problem. These are the kind of problems where you would see the number of choices of filling up any particular place doesn't impact the number of choices for other places. It might not always be the case, but the main crucial fact is that the choices are independent and you need to fill all of those places. Since you need to fill place 1 and place 2 and place 3 all the up to well. In this case, say for example, you have 3 places to fill over here. You might have some question where you have 10 places to be filled, and each one of those places have certain number of choices. Let's say the number of choices for every place is n, and the number of places to be filled is m, and every one of them can be filled in n ways. Total number of possible ways in filling up m-digit number is n to the power m. That's all about this problem. Before moving on to the next variant of problems, we should learn an important concept called factorial. Let's have a look at that. So let's say we are given n, a natural number. N factorial is defined as the product of 1 times 2 times 3 times 4 times 5 times 6 all the way up to n. So let's try to compute a few factorials. 1 factorial is 1, 2 factorial is 1 times 2, that's 2, 3 factorial is 1 times 2 times 3, that's 6, 4 factorial is 1 times 2 times 3 times 4, that's 24. Similarly, 5 factorial is 1 times 2 times 3 times 4 times 5, that's 120. Also, if you guys have noticed, 5 factorial is 1 times 2 times 3 times 4 times 5. This itself is 4 factorial times 5. We can also write the 4 factorial as 3 factorial times 4 times 5. So in general, we can write n factorial as n minus 1 factorial times n. Similarly, we can break down the n minus 1 factorial as n minus 2 factorial times n minus 1 and times n. Also, in many cases we would come across 0 factorial. So for convenience of calculations, 0 factorial is regarded as 1. We would take a look at lots of problems involving factorials in the upcoming courses and the upcoming lectures. So let's summarize the key concepts in this particular slide. The type of problems that we did in this current lecture all have the form m to the power n. Usually there are n places to be filled, and each of those n places can be filled in m ways. Since you need to fill all of the places, so there's n over here, and that's why we need to take the product of m n time, and that leads us to m to the power n. Please do not memorize the formula. That's the entire goal of these set of lectures. Combinatorics is such a beautiful subject
all the problems have a certain underlying theme. From the problems, we try to derive the theory or try to understand the principles. Think about this. If there are like n objects in a shop and every object can be selected in m ways and you need to select all the n objects. You remember the first problem that we did in our second lecture? Picking up 5 plates and 4 bowls from a shop. How many ways are possible to pick 1 plate and a bowl? Similarly, over here there are n objects and every object can be selected in m ways. How many ways can you select all the n objects? There are n objects. And each of them can be selected in m ways. Obviously, you need to select all the objects, hence and since they are independent, the choice of selecting one object doesn't affect the number of ways. The number of ways of selecting one object doesn't affect the number of ways of selecting another object, hence the choices are independent. Hence, the answer is m to the power n. This problem and the problems that we did in the current lecture of form m to the power n are pretty much the same. We just rephrased or translated the language of the problem from one to another. We will be doing a lot on factorials in the upcoming lectures, but for now you could try computing, playing around with factorials. Try your hand at computing, 9 factorial, 10 factorial.
That's all for this video. We will look at more such key concepts in the upcoming videos. If you like the content, show some love. If you have some suggestions for improvement, please comment down below. Feel free to ask your questions, your doubts. Please like and share the video with your friends. Subscribe to this channel and stay tuned for the next one.